Great. Okay. Hello, everyone. My name is Will Crichton. I'm a postdoc at Brown, and this is joint work with my advisor, Shriram Krishnamurthi. And so this paper started from the following question. How are we going to be writing our papers, blog posts, and textbooks, and so on, in 10 years' time? And as computer scientists, we don't just write papers, we program them. And I'm thinking about this because I personally am very dissatisfied with how we program documents. Like, I don't know, just think. Are we still going to be using LaTeX in 10 years? Can we call ourselves programming languages researchers if we're using an unhygienic macro system in the year 2034? That would be shameful. So maybe, we'll upgrade to a modern document language, like Markdown, something more civilized. A language with no programming features at all? Are you crazy? We might as well write our papers in Microsoft Word. But if it's not LaTeX or not Markdown, then what? Are we going to be using PHP, React.js, Perl? You tell me. Like, there's so many document languages out there in the world. And we don't have a good vocabulary to really evaluate or compare these languages. Like if you asked me, what is the essence of a document language? What are the key ideas that we want to keep or throw away in future document languages? There was just not a lot of work on these questions. In fact, the last time someone published anything related to document languages at POPL was in 1980, 44 years ago, when Brian Reed wrote a paper about a language called Scribe. Fun fact. So, nearly half a century later, I felt that it was high time to revisit all of these languages and ask, what is the essence of a document language, at least from a computational perspective? And so I went about answering this question first by organizing the world's existing document languages based on their computational capabilities. And that organization is the first big takeaway from the paper, summarized in this table that there's a lot of detail in, so we will walk through it row by row. So there are two axes to this classification. The first is the domain, or the type of value produced by a document language, and the constructor, or the mechanism for constructing values in the domain. So the simplest document domain is strings, and the simplest constructor is literals. So text files and quoted strings are both examples of string literal document languages. A literal does not permit any computation, and so the next level up is a program. Any traditional language with a string API can be thought of as a string program document language. If you can concatenate the two strings, hello and world, that's a string program. But things get interesting when we try to interleave computation into content. So the simplest form of this is the string template literal, or more commonly a format string. So a template literal allows the interpolation of expressions only. So in this JavaScript example, we use the $brace syntax to pull that variable into the string. But note, the variable binding is still outside of the template literal. And then template programs are template literals with support for other kinds of computation as first-class template features. So in this example, this is the Jinja templating language, which has this brace % syntax for including statements like variable assignment. And besides bindings, you'll also find stuff like conditionals and loops in template programs. So these are the four kinds of constructors, all in the domain of strings. You might notice, for instance, that I put PHP in this category, which might seem a little weird, right? PHP is used to generate HTML, and HTML is not just any kind of string. But the key idea is that these templating systems, these document languages, are not aware of the structure of the things that they're generating. PHP does not inherently know that it's generating HTML in the way that is true for article document languages. So the article domain is document languages that produce trees, specifically tagged attributed trees, like browser documents. And so Markdown is an article literal language, because a Markdown program is effectively a fancy concrete syntax whose abstract syntax is just HTML. There's no computation. An article program language is a programming language that supports constructing articles, like JavaScript's DOM API. And hopefully from here you can kind of start to extrapolate a little bit, right? Like an article template literal is a document language whose terms evaluate to an article. It contains templates that can only interpolate expressions. And examples of this would be things like the JSX syntax for JavaScript or the Scribble dialect of Racket. And finally, article template programs are article templates with support for other kinds of computation, like let bindings, first class in the template. Okay, and so this taxonomy, I think, is a useful way to conceptually organize document languages. It's useful because each category corresponds to many instances of real-world examples. So someone who's designing a new document language can systematically enumerate the design space and ask which of these 8 levels makes sense for my use case. All right, but we still have yet to say precisely what does it mean to be like a string template literal. And that's where the model column comes in. Our core calculus for documents is a sequence of formal models which correspond to each of these levels, each pair of domain and constructor. And each level is defined as an extension of the previous one, so we can clearly demarcate the unique features at a given level. And there, in the remainder of the talk, I will give you a sense of the calculus by walking through each level in the string domain. All right. So the first 2 levels are not interesting computationally. The string literal language is written as this. Expressions are string literals, and the only type is strings. And we add these little annotations to indicate which level a definition applies to. Then the string program level is just system F with a base type of strings. Standard programming language with a string API. The only notable aspect is, again, it's just that the levels are defined with respect to the previous one. But the string template literal language is where it gets more interesting. This is an extension of system F that contains templates. So for example, this template string expression in the concrete syntax of JavaScript would parse into this abstract syntax. So a template would be this list, x, b, x, and it's wrapped in this stir tuple constructor. And formally, a template T is a list of template parts, P. A template part P is either a string literal S or an interpolated expression E. And the stir tuple constructor is a new kind of expression. So that's the syntax of a template, and we'll define its semantics by desugaring it into the base calculus, so system F. And we'll describe the desugaring with this notation, bo sub alpha, that translates from syntax of kind alpha to an expression. So for example, we can desugar the string literal template parts to themselves, and we can recursively desugar interpolated expressions. Now the interesting question is, how do we desugar templates? So here's one simple semantics that we could use. In this semantics, a template desugars into the concatenation of the desugaring of its parts. And then the stir tuple construct is just a no-op. This is totally reasonable. It's actually quite close to the real semantics used in languages like JavaScript. But we're going to see how this style of semantics is difficult to incrementally evolve for later levels. So we'll use a different style that more neatly decomposes each step of constructing the final string. So instead, a template will desugar to a list rather than a string, and the desugaring will follow this familiar inductive pattern. Base goes to base, and then if you are desugaring a p cons to ps, then that desugars to the desugaring of p cons to the desugaring of ps. And then finally, once this generates a list, we have to do more work at expression time to then join this list back into the final string. So a little bit more work. But we need it to cleanly define the string template program language. And so we're going to make 3 additions to our collection of template parts. We can have a set binding from x to e, an if template, if e, then t1, else t2. Those are templates in the branches. And then finally, a for each e x dot t. So the semantics of set are that it desugars to a let binding in the context of the rest of the template. All right? It's a bit subtle because we cannot desugar a set binding independently as its own template part. we need the context of the rest of the template to describe how it desugars, and so this is a special case of the template level desugaring. And once you wade through the notation, you might think this is a little obvious, right? But part of the point here is to give a clean reference semantics. Like, one implication of this semantics is that a set binding within a nested template is going to be scoped to that nested template. But widely used template languages like Jinja and Liquid are actually inconsistent on this point. They have different scoping rules for if templates and for each templates, which is, I don't think, a desirable behavior to preserve in a core calculus. All right, now let's skip to for each loops. A naive desugaring of a for each loop would look like this. For each x.t becomes a map of lambda x dot desugaring of the template and applied to the desugaring of e. This is not right, because a string template needs to desugar to a one-dimensional list of strings, and this map would produce a nested list. One solution is to borrow from quasi-quotes, and if we add some kind of splice construct to our template part language, then we can desugar to that and ensure that our list dimensionality remains one-dimensional. Or alternatively, you can use well-typed nested lists with recursive types and then flatten it later. You can find both of these strategies in string template program languages. Okay, and so that's the essence of a string template program, or at least a sample of it. Hopefully now, if you want to implement your own document language, you have a clearer sense of how to do it. Now, of course, there's more to the document language or the document calculus than just this. If you check out the paper, then we'll give a semantics for the article domain. We show how the document calculus can be extended to model 3 interesting capabilities, mainly references, reforestation, and reactivity. We give a type system for checking templates at the surface level rather than the desugared level, which can be desirable for things like better diagnostics, or as we'll see later, in the case where templates are not just a sugaring for something beneath it. And then finally, in the artifact, we have an OCaml implementation of the calculus, which is implemented with extensible variants to neatly match the formal presentation in the paper. All right. Now, just to wrap up, I want to discuss how the document calculus can be useful in future work. I think there are a number of you who watched this presentation and went, all right, well, it's nice that someone put template semantics down on paper and it seemed pretty straightforward, so I guess that's it. Case closed. But please, my friends, that is the wrong mindset. You're thinking like a PL theorist, but you need to be thinking like a front-end web developer. Let me show you what is happening out in the wild world of JavaScript. That's right. Oh, no, that's right. I say that to myself every day. All right, so here's the idiomatic way that you would generate a bulleted list in the reactive UI framework React. You would interpolate a map expression, and inside of the map, you would return a nested template. Here is by contrast, the idiomatic implementation in the solid framework. Instead of a map, you use a library level for each component. And for yet another contrast, here is the idiomatic implementation in the svelte framework. This uses a language level for each syntax. And so if you were to use React, then these other approaches could be implemented as syntactic sugar for the interpolated map expression, which is how I've described all of the document calculus features in this talk. But what's interesting is it's not true in the other directions. So if you were using solid.js, then the interpolated map is expressible, but would give worse runtime performance than using the for each component. And if you're using Svelte, neither approach is even expressible, given how Svelte desugars its templates. I do not have time to explain to you the details of all the JavaScript frameworks, but basically it comes down to how each framework tries to either statically or dynamically analyze the structure of a template so as to improve the performance of reactivity. Svelte is the most aggressive at static analysis and hence the most restrictive in its desugaring. Now this is just one example, but the bigger takeaway is that for reactive UI frameworks, template design is starting to affect performance, correctness, and expressiveness, not just ergonomics. And in working with these frameworks myself, I have found all of these interactions are rarely documented or even understood by the framework authors. And so my hope going forward is that the document calculus can provide a useful theoretical foundation for reasoning about these more sophisticated kinds of trade-offs in cutting-edge document development. All right, that's it. Thank you very much.
Thank you, Will at Brown. You made your presentation using the calculus, right?
Sadly, this was Keynote, but I'm working on it. I'm working on it.
Hi, Will. Thank you for the very entertaining talk. I'm curious, you talked about the typing rules for the documentation core calculus. Do you think it's important or relevant to have typesetting rules in a document core calculus? Thanks.
Yeah, so there's a really big question here about defining the semantics of a document language with respect to the document, like the semantics of a document in terms of how it would render to a person and whether it would satisfy certain visual constraints, like a document always renders well would be a nice theorem you could prove about a document language. And I think that's a long-term direction I'd like to go in, but I think part of the challenge is there's just absolutely no theoretical basis to start to investigate those questions. And so I'm just trying to figure out, I guess, an angle on that problem such that there's like meaningful theory, but it also corresponds to real human perception. So you would read a document and go like, oh yeah, if this theorem is true, I actually think this document might be readable. So definitely a good point of investigation, but there's just a lot to be done in terms of like even just characterizing what is a readable document. That's a big open question. Yeah.
Hey, thanks. So you talked about compiling down to each of the languages in the right bracket. What about interoperability with them? So if I still have to link with a library or use an existing language ecosystem in my new language in 10 years' time?
Right. So if are you talking about?
If I want to move away from a language, I need to be able to compile down to it so others can use my code.
Yeah.
And also I need to work with existing libraries because if I want to...
Sure.
Yeah.
Right. Well, the nice part about a desugaring based semantics is you can desugar it and then you have something that is probably easier to interchange. I mean, the key thing that you need to interchange is the data representation. I think so a string everyone will share, but like an article or some kind of structured tree is you have to do more to agree on what, like, HTML, for instance, is. I think that's the main point of contention if you want to, say, share documents between different runtimes. But just in terms of the computational stuff I described can really be just thought of as like niceties for generating a document on your own. They wouldn't really affect how easy or hard it would be for you to interoperate either with libraries or others. That's not true once we're talking about these reactive UI frameworks I talked about, because they make foundational assumptions and don't work well together. But that's also like a whole nother research problem.
Yeah, they might not even work well with your compilation model, right? So you might assume something about your generated code that library breaks, and LaTeX would do that, right?
Yes, they could absolutely do that.
Let's get one last question in.
After doing this work, what do you feel are the trade-offs, or what would you prefer for having notations that more obviously desugar into a general-purpose language versus the more specialized case of templates where there's still some understanding of a different sublanguage left after you've parsed things?
If I understand exactly the question, I mean, I think like my ideal document language would be something like you take a robust host language and you embed one of these template notations, template DSLs within it, and they are sort of free to nest within each other as far as you need to go. Because the main thing, if it's just syntactic sugar, again, we're ignoring these expressiveness concerns. If it's just syntactic sugar, then the goal is to make it as easy as possible to write down, like a bold tag if I'm trying to write a document or something like that. And that is just purely a notion of syntax, which we don't cover in this paper, but is quite important. Really, and that's, so I guess just as one example, like I am...
Wrap up quickly.
Oh yeah, I will wrap up very quickly. I am working on a document language that is basically taking these ideas and putting them within JavaScript. So you can write something that looks like Markdown, you can go back into the general purpose JavaScript and just do normal computational things whenever you need and then pop back in recursively. I think that's my ideal future, rather than like some totally standalone DSL like LaTeX that has to have its own totally separate computational model from some not based on any like widely known programming language.
Thanks.
Thank you very much.
All right, yeah.